Well, hey, welcome to Doc Unco's Physics Tutorials. Keith Unco here. Today what we're going to be looking at is the concept of total internal reflection and something called the critical angle when it comes to light passing from one medium into another medium. So we've looked at Snell's law in the past, and we know that from Snell's law what happens when light passes from one medium into another medium at an angle other than 90 degrees, the light is going to bend or refract. Okay, so what we want to look at today is what happens when a light ray coming from, say, a medium like water hits a surface, and what happens after it hits that surface. And what we're going to be looking at is, in particular, what happens when, let's get the pencil going there. What happens when we're looking at this angle theta here, right? And this is going to be theta 1. And theta 1 is the angle that the light impacts the surface at, and here's our surface between the water and the air. Normally what's going to happen to that light is that it is going to go out here at some angle, right? And that's what we would expect. But in this particular case, right, if the angle theta 1 is large enough, something strange is going to happen. Okay, so let's take a look at that. Well, the value of n for, let's do that in black. The value of n for water is about 1.33, and the value of n for air is about 1. Okay. Whoops, make that one a little bit better. So, and let's assume that theta 1 down here is, we're going to make it 49 degrees. Okay, so a fairly large angle, right? And let's see what the angle is going to be that, using Snell's law, that the light should be refracted at as it goes into the air. Well, N1 in this case is going to be 1.33. And the angle is going to be 49 degrees. So times the sine of 49 degrees. It's going to equal N2, which is 1, times the sine of theta 2. And, theta 2, again, is going to be, right, it's going to be this angle in here. Right, that's going to be theta 2. And we expect it to do something, right? So let's see what we get. Well, the sine of 49 degrees is about 0.754, okay? And if we multiply that times 1.33, we get 1.0037, which is going to equal 1 times the sine of theta 2. Well, if you're astute at sines and cosines and sines of different angles, you're going to notice right away we have a problem. And that the greatest value that the sine of any angle can be is 1. Well, we have 1.0037. And if we try and figure this, what theta 2 is, using the inverse sine function on our calculator, we're going to get something called a domain error. It's not going to work, okay? And the reason for this is that what actually happens when an angle that the light hits coming from one substance into another is great enough, instead of that light actually going into the other substance, in this case going into the air, what happens is that light actually reflects back down into the water, or whatever that substance is. Could be water, could be glass, plastic, diamond, could be anything. All right, it's going to reflect back down. Okay, so in this case, all right, the angle theta 1, 49 degrees, all right, is the angle of incidence for the surface up here, right? And I'm not going to be able to do this now. The angle that this beam reflected at should be 49 degrees, and it's not drawn very well there. See if I can draw that again here. That beam actually reflected at the same angle, and this angle should be 49 degrees. that it reflects at. Okay, so it's called total internal reflection because the angle theta 1 is too large, right, to meet Snell's law. Okay, so mathematically it cannot work. And so what happens is this light gets totally internally reflected. Now, there is some technology that we use every day now that actually uses this. And if you have cable TV, which I think we all have, the signal comes in through fiber optic cable. And the way that a fiber optic cable works is, if this is our cable here, all right, the light in the cable actually bounces from one side of the cable to the other side of the cable as it is going through the cable in some direction. Okay, the cable it clearly can't be perfectly straight. You know, it has to bend in certain places. And using this concept of total internal reflection, right, if the angles are great enough, and they make it so that they are, that light will just continually bounce off the glass sheathing, and it will send a signal at the speed of light. Okay, so it works pretty nicely. Now, there must be an angle, all right, in here called the critical angle, at which the light cannot escape from the medium. Okay, in this case, the medium would be glass. And what happens is, when the light cannot escape from the medium, I'm going to draw this in a different color here so we can see it. When the light hits this point right here, instead of leaving the medium, it simply skims the surface. Okay, so the light, this light ray here, is going in this direction. Okay, hits this point right here. I'm making a big circle there. And instead of either being reflected or refracted out into the air, it simply skims the top of the medium. And so what do we have as an angle for refraction? We have 90 degrees. Okay? So if we're looking for what that critical angle is here, so that this light just skims the surface up here, right? Just skims the surface, we can do that again using Snell's law. So let's come down here a little bit. So again, what I'm going to do is I'm going to draw this. I'm going to draw this reflected, or not really, reflected ray here as it just skims the surface. So it doesn't really reflect and it doesn't really refract. It doesn't reflect down back into the water and it doesn't refract out into the air. Okay? And again, this angle up here is 90 degrees. Okay, so using Snell's law, N for the water is still 1.33, N for the air is 1. Okay, we're looking for what this critical angle is down here that will cause the ray of light not to escape the not to escape the water. Okay, so the left side of our equation, Snell's law here, is going to be the side that's in the water. Okay, so we're going to have 1.33, and I apologize if I said glass before I meant water. 1.33 times the sine of theta c, which we don't know, we're going to try and figure that out, is equal to N2, which is 1, times the sine of 90 degrees, because that's the angle at which the light bent. Okay, so the right side of our equation is simply 1, because the sine of 90 is 1. All right, if we divide each side by 1.33, we get the sine of theta c is equal to 1.33. Okay, now 1 divided by 1.33 happens to equal 0.7518. All right, and if I take the inverse sine of that, what I'm going to end up with is 0.7518. I get an angle, theta, equal to 48.746 degrees. Okay, so when this angle theta here is 48.746 degrees, what's going to happen is when this ray of light, this red ray of light up here, hits the boundary, the ray of light is not going to escape into the air. It's not going to be reflected back into the water. All right, it's simply going to skim the surface, and that's known as the critical angle. It's the angle at which the light does not escape at all. It does not escape, and it does not reflect, called the critical angle. You can get a critical angle for any type of material. It can be water, it can be glass, diamond. One of the reasons that diamonds sparkle so much is due to the total internal reflection of light inside the diamond. So I hope that helps, and we'll see you next time.